Assalamualaikum. My name is Najah binti Ma'din and I will present about the introduction. So in this introduction, I will present about the definition of pH, the natural pH indicator, and also briefly explain about the acid-base titration and why we choose onion as the natural pH indicator. In 1909, the Danish biochemist defined the pH stand for the first P stand for the power in German term, while the H is stand for the hydrogen element in the periodic table. While for the definition, pH is a logarithmic measurement of an aqueous solution hydrogen ion content. Okay, so when we want to calculate the pH value, we need to know the concentration of hydrogen ion, and we need to use the base 10 logarithm to calculate the value. pH indicator is a substance that alters hue in solution over a constrained range of pH value. pH indicators are organic molecules that color differently depending on how acidic the fluid they are dissolved in. The most popular technique is as shown above, which is a pH meter. It consists of a reference electrode and a pH sensitive electrode. The different pH values cause acid-base indicator to change hue. Okay. Meanwhile, for the natural pH indicator, usually we use the primarily sourced from plant to determine whether a substance is acidic or basic. As stated by Libertex that acid-base titration is used to find the amount of a known acidic or basic substance through acid-base reaction. Okay, the analyte is the solution with an unknown molarity, while the reagent is the solution with a known molarity that will react with the analyte.
The article review parts is firstly the red onions has been found to be the color of their own skin that contains anthocyanins from the epidermal cells of the scale leaves of the bulb. It is considered as the most biologically active compound that contributes to high antioxidant potential. In anthocyanins, there were acylated and non-acylated in it. Onions contain different types of anthocyanins such as cyanidin, delphinidin, and petonidin. The concentration and type of anthocyanins in onions can vary depending on factors such as the onion variety, maturity, and growing conditions. Among all of the anthocyanins reported, cyanidin derivative was the most frequent in different red onions. Onions contain antioxidant compounds that show their protective effects against chronic disease. To enrich the crude pigment, conventional and non-traditional extraction procedures have been described for anthocyanins. In research studies, anthocyanins actually are unstable and to be oxidized under various factors such as pH, temperature, and enzyme or UV radiation. It will cause color change and degradation. During the extraction, we should find and use the healthiest onion among others to ensure the abundance of anthocyanins. Thus, with the procedure of extract, onion could be used and function as a pH indicator due to the sensitivity and unstable pigment that will occur color changes which could be related to the pH value. Titration is used to determine the concentration of analyte by using the method of quantitative chemical analysis. It focuses on the eco-friendly natural pH indicators that could help reduce the environmental issue. Chemical substances possess an apparent change in color of the analyte and titrant a reacting mixture very close to the point in the ongoing titration known as indicator, which helps to examine and determine the equivalence point in acid-base titrations. While for pH, it could be observed by the natural dyes and pigment in plant due to the fact that they are highly colored substances that show color changes for different pH levels. It requires the plant to have inorganic and organic compound such as flavonols, acylated flavonoids, and anthocyanins, and so on, to be in charge of the color property of plants. Red onions have been used as a type of natural indicator, as it could have the the color changes for different pH values. It contains anthocyanins which have pigments that react to acidic substances and basic substances. It has a purple liquid for the red onion, but it will undergo color change when react with acidic substances from purple to red, while it becomes green when reacted with basic substances. According to one researchers, they compared the results obtained during using the onion extract as a pH indicators with those obtained using a synthetic indicator, which is phenolphthalein. They found that the onion extract produced similar results to the phenolphthalein, and that the use of onion extract as a pH indicator was a student-friendly and cost-effective alternative to the synthetic indicators. Nowadays, sustainable packaging such as natural colorants was used as a colorimetric bioindicator. Some research of scientific literatures shows that bioindicators are actually related to the use of colorants for pH dye indicator applicants. Many kinds of natural colorants were used as natural dye indicators, as they need to have characteristics that contain either curcuminoid, carotenoid, or anthocyanin. Mostly onion has been used due to its shell also consisting of quercetin, which is also important to an antioxidant that could help lead to the color transition of acid and basic solutions. Red onion shows that it could extract colorants such as flavonoid and anthocyanin easily. Thus, it is suitable as a natural pH indicator.
This is the process and materials of preparing onion extract. If the process is done in the lab, the materials needed are onion, cutting board, tripod stand and wire gauze, beaker, distilled water, knife, Bunsen burner, conical flask, filter funnel, filter paper, and glass rod. However, home appliances can also be used. Wash the onions thoroughly to discard soil and impurities. Then, using a clean cutting board and knife, cut the ends of the onions and discard it. Next, safely cut the onions into small pieces without removing the skin, as the skin contains the most anthocyanin. Place the cut onions into a glass container or preferably a beaker. Then, add distilled water to the beaker or glass container until all the onions are submerged. Next, boil the materials for 10 minutes and stir occasionally using a glass rod while heating. This is the fast-forwarded video during a 10-minute process. process, where the color of the extract changes from clear to slightly pink. And then, remove the pickle from the heat and allow it to cool down while soaking the onion for 30 minutes to avoid overheating and the loss of anthocyanin pigments. Finally, using a sieve or preferably a filter paper, filter the onion pieces from the onion extract by pouring it into the filter or sieve. So the onion extract is in a light pink color. So this is the onion extract that is obtained from only 2 onions that can be used as a natural acid-base indicator. These are the titration materials and process. The materials used are HCl, NaOH, acetic acid, onion extract, pipette, burette, conical flask, burette stand and dropper. Firstly, pipette 20 ml of hydrochloric acid with a molarity of 1.0 into 2 conical flasks that is labeled as flask A and flask B. Using a dropper, add 10 drops of onion extract to the hydrochloric acid in flask A and flask B, and it will be used as the natural pH indicator. Fill the clean burette with the sodium hydroxide with a concentration of 0.2 molar until it reaches the 0 mark, which indicates 50 ml of solution. Make sure that there is no air bubble in the burette and measure the initial reading. Then, place the conical flask under the burette and begin to titrate. During the titration, swirl the conical flask continuously to see color change. The solution becomes a lighter pink. As the sodium hydroxide is insufficient, another burette is filled with the sodium hydroxide until it reaches the 0 mark again. And then, the titration is continued with the refilled burette. At this stage, the color of the solution is still pinkish, which shows that the solution is still acidic and it has not reached the neutral state yet. At this stage, the solution is getting less acidic and neutral as the onion indicator is changing to colorless. To ensure the color of the solution, it is checked with a white background. The endpoint is obtained when it changes to slight yellow or green for 30 seconds. Record the final reading of the burette and repeat with the second sample. So for the second sample, the same substance and method was used as the first experiment to get a more accurate result. Since the molarity and volume of acid and base is known, we can calculate the volume needed to achieve the neutral state, or called the endpoint. According to the figure shown, the hydrochloric acid have a molarity of 1.0 molar and the sodium hydroxide have a molarity of 0.2 molar. Since the volume of acid used is 20 ml, using the formula of M1V1 and 2V2, the volume that should be used is 100 ml for the sodium hydroxide. Based on the first titration, we use 99 ml of sodium hydroxide to achieve the endpoint, and let's say if the hydrochloric acid molarity is unknown, and by calculating through the formula of MAVA and MVVB, the molarity calculated is 0.99 molar for the hydrochloric acid, which is only 0.01 molar less than the supposed result. So the onion extract is quite accurate in detecting the pH of solution. As for the second titration, we use 100.1 ml of sodium hydroxide. Using the same method of calculation, the molarity of hydrochloric acid calculated is 1.001 molar. Hence, it is only 0.001 molar more than the supposed result based on the theory. To conclude, based on the first and second titration using the hydrochloric acid and sodium hydroxide, the onion extract works similarly and as accurate as synthetic pH indicator.
Going on, for the next part, we prepare 2 conical flasks with CH3COOH 0.2 molarity solution using pipettes, and the onion extract was being added into it. Thus, the solution will become pink in color due to its acidity. Both conical flasks was being labeled with A and B. After that, we fill the burette with 0.2 molarity NaOH solution until it reached the line of zero level. It's total of 50 ml NaOH in the burette. The conical flask A was left under the burette stand to ensure the titration process. We can see that the drop of NaOH solution was dropped from the burette into the conical flask. At the same time, the white paper was placed to ensure the color change could be shown clearly. After a few times, the color of solution started to change. As we can see, it's a bit more colorless compared to the pinkish color a few minutes before. We decided to close the burette as the color had turned into colorless. And now we can see that the measuring line in burette is about 9.2 ml. By using the formula MAVA equal to MBVB, the calculation was shown as below. So we can get the result answer with conical flask A containing the molarity of 0.092 molarity. Same for the conical flask B, the burette was filled with 15 ml of NaOH 0.2 molarity solutions. The conical flask B was placed under the burette rack and the titration starts when the drop of NaOH starts dropping. After a few minutes, the color change occurred as it became lighter pink and getting colorless inside the conical flask. Lastly, as a result, we show that the reading on burette shows that it's at 10 ml. By applying the same formula MAVA equal to MBVB, the molarity on the conical flask B was shown as 0.1 molarity. And this is the result picture that can clearly see both conical flasks will undergo color change from light pink to colorless after the titration process.
I doing colorimetric experiment to determine the concentration of analyte through comparing the color changes of the solution. So our onion peel is extraction, and also we already have the solution here. This one is a distilled water, 0.1 acetic acid. This one is HCl. This one 1 acetic acid, and this one is NOH. So I'm going to add a few drops of our solution, which is this one, our onion peel extraction, to this chemical here. So we're going to see what the reaction we're going to do. Okay, so now this one is a droplet. I will take a. Now I'm going to, this is distilled water, we're going to add a few drops here. These are the reaction once we add our onion peel extraction into our distilled water. Okay, now for second, I'm going to add into 0.1 m acetic acid. So this is a 0.1 m acetic acid. Okay, going to add a few drops here. Okay, so here we can see there's a bit of changes of color. Okay, in 0.1 m acetic acid. And for third one, I'm going to add the onion peel extraction to HCl chemical. Ini warna apa? Okay, so this one for HCl, we can see there's a massive change for change of colors. Okay, and this one is 1 m acetic acid. Okay, I'm going to add a few drops of our solution. And these are the color changes for the 1 m acetic acid once we added a solution or solution. And lastly, I'm going to add a solution for the 1 m NaOH. Okay, I'm going to add a few drops. Okay, so these are the changes for the 1M NaOH. So once we added our solution, we can see there's a yellow color changes for this 1M NaOH. So this is the result once we added the solution to our chemicals. Okay, so the first one will be distilled water. So we can see here there's no changes color here. So this one considered as a neutral, and this one, the second one, is 0.1 m acetic acid. So we can see here there is a light red or light pink. We can see there is a changes of color once we added a solution from a onion peel extraction. So this one considered as a acid, and this one the chemical will be HCl, and also changes color here to a bit red color or in a pink color. Okay, and this one is a acetic acid 1M. Okay, we can see there is a changes color too. Okay, so we can see here for the HCl and also for the and for the acetic acid 1M. Okay, there is no much of different here. We can see there is almost same color. And the last one will be the NaOH. Okay, 1M. Okay, so we can see there is a massive changes color for this part. Okay, so once we added our peel extraction, onion peel extraction, our solution, so this one will be yellow color. So we can see for these three chemical. Okay, so once we added our onion peel extraction, so from here we can know that the higher the concentration, so the greater the color changes.
Okay, Now we will start our discussion. May I ask Zingy to compare our results that we got from doing the experiment in the lab with previous studies?
Okay, for our experiment, throughout our experiment as using the onion for pH indicator, we actually get the result that onion extract, when it mixed with different solution, it will have a color change. So we actually saw that it's like no change for the color for distilled water, but for 0.1 acetic acid, HCl, and acetic acid 1N, it actually changed the color to light pink or reddish pink. But for sodium hydroxide, it actually have the color of green and yellowish color. So we actually can conclude that when it actually contact with the acidic substance, it will become like more pink and reddish color. But for alkalic, it will be more yellowish and green. So, but for neutral, it's actually basically have no color changes. So to compare with the previous study, we have actually studies before. So it actually shows that the same result with our experiment. So, but just the difference that the material using, they'll be using the more daily substance for the experiment, such as like window cleaner, detergent, baking soda, lemon or vinegar. So in conclusion, we can say that the more acidic or basic something is, the darker the color will be. And for our titration part, in the previous study, there is like more use for determining the equilibrium point in acid-base titration. So it helps to determine the concentration of an analyte. In our experiment, we used to determine the molarity of HCl and acetic acid when it reacts with sodium hydroxide. So with using the onion extract to be the pink color mixed with the HCl acetic acid, we actually using the drops of NaOH, the solution will turn neutral and the color change will from pink to colorless. So with using the formula MAVA equal to MBVB, it actually shows that nearly 1 m of HCl and 0.1 m for acetic acid as their molarity. So as both of these experiments were actually using the same method of observing the color change sample in equilibrium points at different solvents. So just the main difference with previous study was the previous study is using actually a different natural indicator, but we use their theory on our onion extract. Yeah, that's all from me. Thank you.
Thank you, Zingy, for the precise explanation. Now, I will explain the implication of our natural pH indicator that we chose, which is onion. I will explain on how the onion can function as natural pH. Onion is an olfactory indicator that it doesn't have odor in strongly basic solution. Red onion can act as visual indicator at the same time, and it changes to pale red in acid solution to green in basic solution. As from our previous research, it shows that red onion contains flavonoids such as cyanidin and quercetin. They are responsible for color changing. And cyanidin-free glyphosate is considered as the major anthocyanin that is found in the most of the plants that is in charge of the color pigments of foods. And also red onion is rich in glyphosate, which are known as the primary flavonoids, and polyphenols such as quercetin glycerol. Okay, from the experiment that we conducted, it showed the color changes according to the substances that we tested on. Therefore, with the help of anthocyanin, the color of liquid will be affected and work as a visual natural indicator by reacting with different substances. Okay, now we already know the onion as natural pH is a very good idea, but we also need to know the limitation that we face in choosing onion as natural pH indicator. Nabil, can you explain about the limitation?
Okay, so my part will be limitation in acid-base titration. So the most common and also the obvious limitation of titration experiments is that the end point of the process does not necessarily equal the equivalence point precisely. So by boiling the onion peel, a class of pigment molecules called anthocyanins will dissolve into the liquid. So where we get the anthocyanins from our onion peel extraction. So anthocyanins become unstable under different environmental conditions, mainly because of pH, temperature, light, oxygen, but they are easily oxidized through. It depends on the pH solution. So this is because of the molecular structure of anthocyanins having an ionic nature. Furthermore, in acidic conditions, some of the anthocyanins appear red. Anthocyanins have a purple hue in neutral pH, while the color changes to blue in an increasing pH condition. But in this experiment, the colors are very light, and that the reason cannot detect the pH value accurately, but can be known as acid or base from this experiment. That's all.
So it wasn't stable enough like the synthetic pH indicator or pH meter. I see. Putri, got any suggestion or recommendation to solve the limitation issues?
I will explain some recommendation for the onion extract. Since the onion extract is easily oxidized, the method that could solve this problem is by storing it in low temperature to avoid oxidation. Besides, we can also try storing it in vacuum container because it helps in avoiding the extract from exposing to the oxygen in the surrounding. These are the conventional methods to overcome the limitation. There has actually been some research made to find methods in utilizing the anthocyanin chemically, and mostly by adding other pigments, but I think, in my opinion, it cannot be used as a pH indicator because the color of the pigments may affect the result of the onion extract during the detection of the pH. Hence, to conclude, the onion extract is indeed one of the most accurate natural pH indicator that can be used to replace the synthetic pH indicator. Since there is no clear research on how to maintain the stability of the anthocyanin without any pigment, there should be more research done in the future, as the onion extract may be used commercially in the future. As for now, the onion extract can be used for household use before it can be expanded to commercial use and used professionally.
Understood well, Putri. Thank you for your answer. Now we might already come to an end of our discussion, but before that, let us have Shakila to summarize our experiment and the discussion today.
Summary of this experiment that I can conclude is that the red onion extract experiment, which acts as a natural pH indicator, is accepted as the experiment shown is successful, even though it has its own limitations. The hypothesis that we made supports our information given in the article review provided. The results show that distilled water has no change in color, while for 0.1 mole acetic acid, it does show light pink color. Other than that, 1.0 mole acetic acid and hydrochloric acid show reddish pink in color. For the basic solution, which is a sodium hydroxide solution, change to green color. The main part of this experiment is the boiling the onion. It is successful due to the boiling of onion in low temperature to ensure the anthocyanin does not disappear and is still in there abundantly. The anthocyanin will determine the color shown for pH value. In my opinion, red onion can be a natural pH indicator in our daily life to replace the synthetic indicator such as phenolphthalein, methyl orange, and methyl red. In addition, benefits using onion is that onion is a natural, inexpensive, and readily available source of pH indicator, which may be particularly useful in resource-limited settings where access to synthetic indicators is limited. I also believe that another benefit of using onion as a pH indicator is its potential use in food science. Synthetic indicators are not suitable for use in some food products as they may be toxic or alter the taste or texture of the food. Onion-based indicators, on other hand, are natural and safe for use in food products, making them an attractive alternative. Furthermore, using onion as a pH indicator may be more environmentally friendly than using synthetic indicators, which often require the use of harsh chemicals and generate hazardous waste. Finally, using onion as a pH indicator may be useful in educational settings where it can be used to demonstrate the principle of pH and acidity to students in a hands-on and engaging way. It is easier for students to understand the pH and acidity in details. That's all from me. Thank you.
Alright, so this is the end of our discussion today. Thank you, Shakila, for your points, and thank you everyone for your time today.